Welcome! In this session, we'll tackle an interesting problem from LeetCode, problem number 976, largest perimeter triangle. The goal is to determine the largest perimeter of a triangle that can be formed using an array of stick lengths. Let's explore the problem and break it down step by step. Let's start by understanding the problem. You're given an array of integers, where each number represents the length of a stick. Your task is to find the largest perimeter of a triangle that can be formed using exactly 3 sticks from the array. If it's not possible to form any triangle, you'll return 0. Now, for a triangle to be valid, it must satisfy the triangle inequality rule. This means that the sum of the lengths of any two sides must be greater than the length of the remaining side. If we sort the sides as A, B, and C such that A is the smallest and C is the largest, then the condition becomes simple: A plus B must be greater than C. Finally, you'll be given an integer array nums with a length between 2 and 10,000, and each stick length will be between 1 and 1 million. The output will be a single integer, which is either the largest possible perimeter or 0 if no triangle can be formed. Let's look at some examples to make this clearer. In the first example, the input array is 2, 1, 2. Here, we can choose the 3 sticks with lengths 1, 2, and 2. When we check the condition for a valid triangle, we see that 1 plus 2 is greater than 2, so the triangle inequality is satisfied. The perimeter of this triangle is the sum of its sides, which is 1 plus 2 plus 2, giving us a total of 5. So, the output for this example is 5. Now, in the second example, the input is 1, 2, 1. For these sticks, the sum of the two shorter sides, 1 and 1, is not greater than the longest side, which is 2. This means the triangle inequality is not satisfied, so it's impossible to form a valid triangle. As a result, the output is 0. Looking at the third example, the input array is 3, 2, 3, 4. Here, we can select the 3 sides 3, 3, and 4. If we sort them, we get 3, 3, and 4, and we can verify that the sum of the two smaller sides, 3 and 3, is indeed greater than 4, satisfying the triangle inequality. Therefore, these sides can form a valid triangle. The perimeter of this triangle is the sum of its sides, which is 3 plus 3 plus 4, giving us 10. So, the output for this example is 10. Now, before we move on, it's important to note the constraints of the problem. The length of the input array will be at least 3 and at most 10,000, and the stick lengths will range between 1 and 1 million. This means the solution needs to be efficient enough to handle large inputs within a reasonable time. Now, let's consider some edge cases you might encounter. First, if the input array contains fewer than 3 elements, it's impossible to form a triangle, so the output should be 0. Second, if all the sticks are of equal length, a valid triangle can still be formed as long as the triangle inequality holds. For example, 3 sticks of length 5 would form a valid triangle. Third, since the input size can be large, the algorithm needs to handle arrays efficiently, ideally with a time complexity of O, n log n. Finally, there may be cases where no valid triangle can be formed at all. This can happen if, for every combination of 3 sticks, the triangle inequality is not satisfied. In such cases, the output should simply be 0. With these considerations in mind, you're now ready to start thinking about how to approach the solution. To tackle the problem of finding the largest perimeter of a triangle that can be formed from an array of stick lengths, we first considered a brute force approach. The intuition behind this method is simple: test all possible combinations of 3 sticks to check if they can form a valid triangle, and then calculate the perimeter for each valid combination. The steps involve iterating over all triplets from the array, verifying the triangle inequality conditions for each triplet, and tracking the largest perimeter. However, this approach has a significant drawback. Since it involves testing all possible triplets, the time complexity is cubic, or O, n cubed, which makes it computationally impractical for larger arrays. While conceptually straightforward, this method is inefficient and would likely exceed time limits for inputs of substantial size. A more efficient solution is the optimized greedy approach. The main insight here is that, to maximize the triangle's perimeter, we should focus on the 3 largest stick lengths that satisfy the triangle inequality. By sorting the array, we can ensure that the largest values are prioritized. When considering three sides, say A, B, and C, the triangle inequality simplifies to ensuring that the sum of the two smaller sides, A and B, is greater than the largest side, C. To implement this, we first sort the array in descending order. Then, we iterate through the sorted array, checking each triplet for validity. If a valid triangle is found, its perimeter is calculated and returned immediately. If no such triplet is found, we return 0. This approach is far more efficient than brute force, as sorting the array takes O, n log n, and the subsequent iteration is linear, giving an overall time complexity of O, n log n. Additionally, this method is simple to implement while ensuring optimal performance. For this problem, we selected the optimized greedy approach due to its balance of efficiency and simplicity. The key realization was that sorting the array allows us to quickly and effectively identify the largest valid triangle perimeter without needing to test every combination. By checking consecutive triplets in the sorted array, we naturally prioritize larger stick lengths and can swiftly determine the solution. When comparing this approach to brute force, the differences are clear. The brute force method, while straightforward, is computationally expensive with a time complexity of O, n cubed, making it impractical for large inputs. In contrast, the greedy approach leverages sorting to achieve O, n log n, complexity, which is much more scalable. While sorting introduces a pre-processing step, the performance gains far outweigh this minor drawback. Overall, this strategy provides an optimal balance of clarity, speed, and correctness, making it the most suitable choice for solving this problem. In this problem, we aim to find the largest perimeter of a triangle that can be formed using an array of stick lengths. To ensure the triangle is valid, it must satisfy the triangle inequality condition, which states that the sum of the lengths of any two sides must be greater than the third side. To solve this efficiently, we use a greedy approach combined with sorting. By sorting the array, we can prioritize the largest stick lengths first, as they are most likely to form a triangle with the largest perimeter. The algorithm begins with input validation. If the array has fewer than 3 elements, it's impossible to form a triangle, and we simply return 0. Next, we sort the array in descending order so the largest stick lengths appear first. For example, an input of 3, 6, 2, 7 gets sorted into 7, 6, 3, 2, making it easier to check for valid triangles in the optimal order. After sorting the array, we iterate through it to examine groups of 3 consecutive sticks. Starting with the largest stick, we label the current 3 as A, B, and C, where A is the largest, B is the second largest, and C is the third largest in the current window. For these 3 sticks, we check the triangle inequality condition, A less than B plus C. If this condition holds, it means these sticks form a valid triangle. In this case, we calculate the perimeter as A plus B plus C and return it immediately, since the sorted order guarantees that this is the largest possible perimeter. If no valid triangle is found after checking all consecutive triplets, we return 0, indicating that no triangle can be formed with the given stick lengths. Let's walk through an example to see how the algorithm works. Suppose the input array is 3, 6, 2, 7. First, we sort the array in descending order, resulting in 7, 6, 3, 2. In the first iteration, we consider the 3 largest sticks, E equals 7, B equals 6, and C equals 3. We check the triangle inequality, 7, 6 plus 3. This condition is true, so these 3 sticks form a valid triangle. We then calculate the perimeter as 7 plus 6 plus 3 equals 16 and return this value. Since we have found a valid triangle, the algorithm terminates early. The output for this example is therefore 16. This algorithm leverages several key insights to ensure efficiency and simplicity. First, sorting the array in descending order allows us to focus on the largest stick lengths first, which minimizes unnecessary checks. The greedy approach ensures that we return the first valid triangle perimeter, guaranteeing that the maximum value is returned without further computation. Additionally, the algorithm uses an early exit strategy, terminating as soon as a valid triangle is found, making it highly efficient. For edge cases, the algorithm handles arrays with fewer than 3 elements by returning 0. Similarly, arrays where no 3 sticks satisfy the triangle inequality also return 0. Duplicate stick lengths are naturally supported, as in the case of 1, 1, 1, which forms a valid triangle. This approach requires minimal data structures, relying only on the sorted array and a few variables, ensuring low space usage. Finally, let's analyze the complexity of the algorithm. The time complexity is dominated by the sorting step, which takes O n log n. Iterating through the array to check for valid triangles requires O n. Combining these, the overall time complexity is O n log n. The space complexity is O(1) if we sort the array in place, or O(n) if we create a copy of the array for sorting. To optimize further, sorting in descending order simplifies the logic by aligning the largest candidates at the start. The algorithm's early exit mechanism also reduces unnecessary iterations by stopping as soon as a valid triangle is found. This balance of efficiency and simplicity makes the solution both optimal and easy to understand, providing a clear and effective way to solve the problem. This solution efficiently solves the problem using a greedy approach combined with sorting. Here's the explanation. 1. Sorting the array is sorted in descending order. This ensures that the largest stick lengths are considered first. Sorting takes O n log n time. 2. Iterating through the array. After sorting, we iterate through the array and check each triplet of consecutive numbers. The goal is to find the first triplet that satisfies the triangle inequality condition. The sum of the two smaller sides must be greater than the largest side. 3. Triangle inequality check. For each triplet nums I plus 1, nums I plus 2, we check if nums I plus 1, plus nums I plus 2. If this condition holds, the triplet can form a valid triangle. Since the array is sorted in descending order, this is the largest perimeter possible with the given lengths. We return the sum of the triplet as the result. For returning 0, if no triplet satisfies the triangle inequality condition, it means no valid triangle can be formed. In this case, we return 0. ### complexity analysis. Time complexity. Sorting the array takes O n log n, and the iteration through the array takes O n. Therefore, the overall time complexity is O n log n. Space complexity. The solution uses O(1) additional space, as the sorting is done in place and no extra data structures are used. ### edge cases. If the array has fewer than 3 elements, no triangle can be formed, and the function correctly returns 0. Arrays with all elements being the same, e.g. 1, 1, 1, are handled correctly, as long as they satisfy the triangle inequality condition. Arrays with a mixture of large and small numbers are sorted to ensure proper evaluation of the largest possible perimeter. This implementation is concise, efficient, and handles all edge cases, making it suitable for production use. This is the Java implementation of the largest perimeter triangle problem using the same logic as the provided Python solution. The array is first sorted, and then the triangle inequality condition is checked iteratively for triplets starting from the largest numbers. The implementation leverages Java's arrays.sort method and includes type declarations required in Java. The solution ensures that the largest valid perimeter is returned, or 0 if no valid triangle can be formed. Here, we start with the input array nums equals 2, 1, 2. The first step is to sort the array in descending order, which gives us nums equals 2, 2, 1. By sorting, we place the largest numbers at the beginning, making it easier to evaluate potential triangles. Next, we check the first triplet formed by the 3 largest numbers, nums 0 equals 2, nums 1 equals 2, and nums 2 equals 1. The triangle inequality condition states that the largest side, nums 0, must be less than the sum of the other two sides, nums 1 plus nums 2. Substituting the values, we check if 2 less than 2 plus 1, which evaluates to true. Since the condition is satisfied, the perimeter of this triangle is calculated as the sum of the 3 sides, 2 plus 1 is equal to 5. Therefore, the largest perimeter for this input is 5. In this example, the input array is nums equals 1, 2, 1. The first step is to sort the array in descending order, resulting in nums equals 2, 1, 1. Sorting ensures that the largest numbers are prioritized for checking the triangle inequality. We consider the first triplet, nums 0 equals 2, nums 1 equals 1, and nums 2 equals 1. The triangle inequality requires nums 0 to be less than nums 1 plus nums 2. Substituting the values, we check if 2 less than 1 plus 1, which evaluates to false. Since this triplet does not satisfy the condition, we move to the next potential triplet. However, there are no additional triplets available in this array. As a result, no valid triangle can be formed, and the output for this input is 0. Now, we examine the case where the input array is nums equals 3, 6, 2, 3. After sorting the array in descending order, we obtain nums equals 6, 3, 3, 2. Starting with the triplet formed by the largest three numbers, nums 0 equals 6, nums 1 equals 3, and nums 2 equals 3, we check the triangle inequality. Does 6 less than 3 plus 3? This evaluates to false, so this triplet cannot form a valid triangle. We then move to the next triplet, which consists of nums 1 equals 3, nums 2 equals 3, and nums 3 equals 2. Here, we check if 3 less than 3 plus 2. This condition is true, so the triangle inequality is satisfied. The perimeter of this triangle is calculated as 3 plus 2 is equal to 8. Therefore, the largest perimeter for this input is 8. The time complexity of this solution is determined by two key operations. First, we sort the input array nums in descending order using Python's built-in sort method with reverse equals true. This sorting step is performed using the timsort algorithm, which operates with a time complexity of O n log n for an array of size n. After sorting, we iterate through the array to check triplet combinations against the triangle inequality condition. The loop runs from index 0 to len, nums 3, which means it executes up to n2 iterations in the worst case. Within each iteration, we perform constant time operations, such as comparisons and additions, which contribute O1 per iteration. Combining the sorting step in the loop, the overall time complexity becomes O n log n plus O n, but since O n log n dominates, the final time complexity is O n log n. The space complexity of this solution is minimal. First, the sorting operation is done in place using Python's timsort algorithm, which does not require any additional memory aside from a constant amount for internal operations. This means the space complexity of sorting is O1. Second, we do not use any auxiliary data structures like lists or dictionaries to store intermediate results. All computations are directly performed on the input array nums. Therefore, the overall space complexity of the solution remains O1. Now, let's consider the behavior of the algorithm in different scenarios. In the best case, the first three numbers in the sorted array form a valid triangle. Here, the loop terminates after just one iteration, resulting in a time complexity of O n log n for sorting and O1 for the loop, which simplifies to O n log n. In the average case, the loop runs for some portion of the array before finding a valid triplet that satisfies the triangle inequality condition. However, even in this situation, the sorting operation remains the dominant factor that determines the overall time complexity. As a result, the time complexity in the average case is still O n log n. On the other hand, the worst case occurs when no triplet in the array satisfies the triangle condition. In this scenario, the loop runs 4n2 iterations, covering the entire array. Once again, the sorting step dominates, leading to an overall time complexity of O n log n for sorting and O n for the loop. Together, this simplifies to O n log n as the final time complexity. Let's compare this optimized solution to a naive or brute force approach. In the brute force method, we would generate all possible triplets from the array and then check each one against the triangle inequality condition. The number of possible triplets is given by the combination formula C n3 equals n asterisk n1 asterisk n2 slash 6, which leads to a time complexity of O n cubed. By contrast, the optimized solution avoids generating all combinations by first sorting the array and then checking the condition in a single pass. This reduces the time complexity from O n cubed to O n log n, making the optimized approach significantly faster. The mathematical justification for the sorting step lies in the properties of the timsort algorithm. It divides the array into smaller chunks, performs linear work at each level, and merges them in logarithmic depth, resulting in a time complexity of O n log n. Finally, let's analyze the loop in the optimized solution. The loop iterates linearly through the array, running up to n2 times in the worst case. Each iteration involves a constant amount of work, such as comparisons and additions, resulting in a time complexity of O(n) for the loop. However, since O(n) is asymptotically smaller than O(n) log n, the loop does not change the overall time complexity of the algorithm. Combining the sorting step and the loop, the total time complexity remains O(n) log n. As for space complexity, the algorithm performs all operations in place and does not require additional memory, keeping the space complexity at O(1). This makes the solution efficient in both time and space, making it a practical approach for solving the problem. When solving the largest perimeter triangle problem, there are some common mistakes to watch out for. First, not sorting the array is a frequent issue. Sorting is crucial because it ensures that the largest elements are considered first, which simplifies the triangle inequality check and maximizes the potential perimeter. Without sorting, you might miss valid triangles or perform unnecessary comparisons. Next, applying the triangle inequality incorrectly can lead to errors. For example, using conditions like a plus b greater than c without ensuring that a, b, c are ordered properly can fail because the theorem specifically applies to the two smaller sides being greater than the largest side. Sorting guarantees the sides are in the correct order, avoiding this mistake. Finally, skipping edge cases like arrays with fewer than 3 elements or arrays where no valid triangle can be formed is another pitfall. A valid triangle requires at least 3 sides, and failing to handle these cases properly might lead to runtime errors or incorrect outputs. Another common mistake is relying on a brute force approach when dealing with large inputs. Brute force solutions, which involve checking all possible combinations of 3 sides, have a time complexity of O(n) cubed. This is computationally expensive and will likely exceed time limits for inputs as large as 10 to the power of 4. Instead, it's important to use more efficient strategies. Additionally, overcomplicating the algorithm is another problem to avoid. Introducing unnecessary loops or conditions can make the solution harder to debug, less efficient, and more prone to errors. A simple greedy approach is often sufficient and ensures clarity and maintainability in your code. To perform well in interviews, it's important to understand the key insights of this problem. Sorting the array and using a greedy approach is the most efficient way to find the largest perimeter. After sorting, you can iterate from the end of the array to check 3 consecutive sides. This not only simplifies the triangle inequality check but also ensures the largest perimeter is found. This problem highlights a common pattern in algorithm design, where sorting helps simplify constraints and reduce the search space. If interviewers ask follow-up questions, such as extending the problem to higher dimensional shapes, focus on adapting the inequality rules and addressing edge cases. Remember, the sorting step dominates the time complexity at O(n) log n, while the subsequent linear pass is O(n), making this combined approach optimal. Additionally, this problem is similar to LeetCode 611, where the goal is to count the number of valid triangles. Both involve sorting and applying the triangle inequality. Other related problems can help you understand variations in this type of approach. For example, LeetCode 16, the three-sum closest problem, involves finding 3 numbers whose sum is closest to a target. Like the largest perimeter triangle problem, it involves sorting and selecting subsets of 3 elements. Similarly, LeetCode 15, the three-sum problem, focuses on finding all unique triplets that sum to 0. This also requires iterating through triplets and selecting valid combinations. Another interesting problem is LeetCode 376, wiggle subsequence, where the goal is to maximize the length of a subsequence with alternating differences. While the context is different, it shares the use of greedy strategies and optimization techniques, which are central to solving problems efficiently. When considering alternative approaches, the brute force method is the simplest to understand. It involves checking all combinations of 3 sides to determine if they form a valid triangle and calculating their perimeter. However, this approach is highly inefficient for large inputs, with a time complexity of O(n) cubed. The greedy approach is the optimal solution. By sorting the array first, you can focus on the largest 3 sides and move backward only if necessary. This method is efficient, with a time complexity of O(n) log n, and is straightforward to explain in interviews. Another alternative is a hashing-based approach, which involves using a hash map to store side lengths and check combinations. While this might work, it adds unnecessary complexity to the problem and is generally not recommended unless specifically required by the problem constraints. Great job! Today, we learned how to solve the largest perimeter triangle problem by sorting and applying the triangle inequality. Remember, these types of problems test both your algorithmic thinking and mathematical skills. Keep practicing, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!